This exercise is about the modes in the hollow waveguide, more specifically in the situation at cutoff. So, what's this about? We have a waveguide with an arbitrary potato-shaped cross-section, which we call S, and we fill that waveguide with air, so refractive index equal to 1, and then the boundaries of that waveguide is just metal. So in essence, we have a funny shaped metal pipe, empty, and then the electromagnetic energy can propagate in several waveguide modes along the axis of this waveguide. Now, the first question we're interested in, specifically for the case of looking at waveguide modes, how does the Helmholtz equation change? Or what is the form that the Helmholtz equation takes in this case? So try and pause the video to figure that thing out. We know specifically for the waveguide mode that the electromagnetic fields can be split up in a part that only depends on x and y. And then for the z dependence, we have exponential minus j kz z. So that's the general form of a waveguide mode. Obviously, this psi over here and that psi over here are different quantities, but because of my laziness, I did not introduce a new notation here. Now, if we have a form like this and we plug that into the Helmholtz equation, which is Laplacian psi plus k squared psi, then this becomes, so for the Laplacian, it's a summation of the second order derivatives with respect to x, y, and z. Now, those with respect to x and y, we're just going to combine them in what we call the transverse Laplacian, so only x and y play a role there. And then we still need to deal with the second derivative with respect to z. Now, every time we take a derivative with respect to z, if you look at this form here, you will pick up an extra factor minus j kz. So we do that twice, so we have minus j kz squared. But apart from that, the form stays identical, so we still have a psi here. So this is what happens to the Laplacian. And now we just add our k squared psi again, plus k squared psi, and that thing should be equal to 0. So cleaning this up a little bit, this becomes the transverse Laplacian of psi plus k squared minus kz squared psi equal to 0. So that's the specific form that the Helmholtz equation takes if you're looking for waveguide modes. Let's now take a next step and let's take a look at what happens in the situation where we are at cutoff. Now, when is a waveguide mode at cutoff for this particular geometry? That happens when the propagation constant kz is equal to 0. Of course, do not confuse this with the cutoff condition that happens in open waveguide, for example, an optical fiber. So for an open waveguide, the cutoff condition is very different. There, that's determined by our propagation constant becoming equal to the propagation constant in the cladding. So here we don't have a cladding, but from electromagnetic theory, we know that kz equal to 0 is the cutoff condition. What are we interested in? We are interested in the value of k at cutoff. So this is what we want to figure out, because this will tell us, for example, what the wavelength at cutoff is. K and lambda are, of course, inversely related. So let's try and figure out something to determine the k value at cutoff. So the k value at cutoff, of course, obeys the following equation: Laplacian psi plus k at cutoff squared, where kz is equal to 0 at cutoff, equal to 0. Now, what I want you to show now is that if we have a variational expression of the following form, so j is equal to the integration over the cross-section of our transverse gradient squared ds, and then we divide that by another integration over the cross-section of psi squared ds. What I want you to show that if you minimize this particular variational expression, you end up with a value which will tell you what the k value at cutoff squared is. So at the minimum, j becomes k cutoff squared. Of course, very important here is to not misinterpret this term here. This is the gradient squared. This thing is not the same as the Laplacian. There the squared is in a slightly different place. So don't confuse these two quantities. So what I now suggest you do is pause the video and try to minimize this variational expression. If you try and do that in the straightforward way, so first of all calculating j at psi and then subtracting j at psi plus delta psi from it, you probably have noticed that you end up with a lot of trouble because you have also psi plus delta psi in the denominator over here, which you should evaluate in a Taylor series to get rid of it. So lots of complicated stuff. Let's see if we can make our life a little bit easier here. So a trick I can show you is, rather than starting from this expression directly, we're going to get rid of the denominator by just multiplying it so that it ends up at the left-hand side. So we're going to start from j times the integral of psi squared ds being equal to the integral of the transverse gradient squared ds. So this is our first equation. What I now want to do is take that equation and perturb it a little bit. So let's perturb it, for example, by taking psi and replacing that by psi plus delta psi. And that change will result in a change in j. So also j will then change from j plus delta j. Where delta psi and delta j, they're not independent, but they're coupled. So this is the delta j coming from this change delta psi. So this is how you should interpret these quantities here. So if we do that perturbation of that equation, we end up with j plus delta j plus delta j, the integral of psi plus delta psi squared ds is equal to the integral of the transverse gradient of psi plus delta psi squared ds. So this is what we get when we take that expression 1 here and perturb it a little bit. And that expression we're going to call expression 2. Now what you can do is you can subtract expression 2 from expression 1, and that way try and figure out what to do with this delta j. So I suggest you do just that. Based on these two expressions, try and minimize the variational expression. One thing you could do is, okay, you subtract these two, you do lots of calculations, and at the end of the day, you come up with an explicit expression, delta j is equal to complicated expression. And then the next step is putting delta j equal to 0 in order to minimize the variational expression. That's one way of doing things. Another way of doing things is saying, okay, if at the end of the day, I'm going to put delta j equal to 0, why not save myself a lot of trouble and already at the beginning put delta j equal to 0, and then use that expression to continue to work with. So if we do that, all of a sudden our equations become a lot more simpler, and our life also becomes a lot simpler if we subtract these two equations. So if we take equation 2 minus equation 1, then what do we get? Well, first of all, let's expand that square here in our minds. So the first term we get is psi squared, which is of course exactly the same term as we have for equation 1. So these two will cancel. Then we have the double product. So the double product gives us j times the integral of 2 times psi delta psi ds. That term does not have any counterpart in equation 1, so that one stays. And then the third term is the square of this delta psi here. That's a higher order term, so we're just going to neglect that as we did earlier. So this equal sign becomes an approximately equal sign. So without too much calculations, we've managed to calculate the difference between the left-hand sides here. For the right-hand sides, the story is extremely similar. So again, we expand the square here. The first term is exactly the same term as appears in equation 1. So that one we don't need to worry about. And then we have our double product. So that's going to be the gradient, transverse gradient of psi, transverse gradient of delta psi ds. And for the third term, again, it's a higher order term. Let's get rid of it. Okay. Let's get rid also of the 2 to simplify things. And then what we can do is proceed along exactly the same lines as we did in the textbook, is use that variation of Green's formula to manipulate that term over here. So that brings us to j, the integral psi delta psi ds is equal to. So we can use exactly the same formula, but since we're working in a 2-dimensional case for waveguides, we just go from a 3-dimensional formula to a 2-dimensional formula. So we have here an integral over the boundary of S of delta psi normal derivative d psi dn dl. Then we have the integral of delta psi Laplacian of psi ds. So again, exactly the same as we did in the textbook for a different case, just 1 dimension lower. And then also, just like in the textbook, in this case, we're going to say that the term related to the boundary conditions is 0, because we have a perfectly reflecting metal container, which will just kill all the fields there at the boundary. So this is going to be 0. And then finally, we can bring that term back to the left-hand side, so that we can write down that we have the integral of, and then let's factor out delta psi, the integral of delta psi. Then we have the transverse Laplacian of psi plus j psi integrated out over the cross-section is equal to 0. Now the crucial part here is that this thing should be true for all possible variations delta psi that you can think of, because that's just an arbitrary variation. So the only reason that this can be true, the only way this can happen, is that if this expression here between square brackets is also equal to 0. Therefore, we can conclude that if we minimize our variation expression, that the corresponding Euler-Lagrange equation looks like this. Now, if we go back to the equation that we were interested in the beginning, you can easily identify that this j here is actually the k value at cutoff squared, which is what we needed to show, that minimizing that variation expression gives you a value for k cutoff squared for this particular waveguide. Before we leave, just a final remark here. So we've shown that the j, so the variation expression for k at cutoff squared, is equal to the following expression, psi squared ds divided by the integral psi squared ds. Now in the textbook, we've also introduced another variation expression, this time for the energy in a mode. Now that expression looked as follows. So this was the gradient squared minus k squared psi squared dv. Now in our particular case, since we're A, working with waveguide modes, and B, working at cutoff, we can do a similar reduction in dimensionality to say that in our case, This is going to be a two-dimensional integral of the transverse Laplacian, just like we did in the beginning of this exercise, minus k squared psi ds. So this will give us the energy at cutoff, because remember, of course, we're working here with k at cutoff. Now, if you compare this expression with that expression over here, so if you just substitute the value for k at cutoff in that equation, then these things all cancel. So the conclusion is that at cutoff, the energy in that waveguide mode actually vanishes.